We have mentioned controller design with exam model knowledge. And today, we will extend the same model but with unknown parameters. Model knowledge is not available. Then the approach or the controller to be designed to deal with this property is high gain control and high frequency or adaptive control. So today, at the beginning, I will first quickly go through the material we covered last time, so give you a recap. We say that we consider this kind of Euler-Lagrange system, which is like a robot arm system. A single joint, so the Q here is a scalar, and the parameters are known. They are constants. The states and the time derivative of states, which are the angles, are measurable. So everything here is known. And we try different Dilbert functions. We try 3 different Dilbert functions. Only the third one works, but it requires using a filter tracking error here. So R is defined as E dot plus alpha E. Alpha is also can be considered as a control gain. So the property of this R with E and E dot is that if R is bounded, both signals will be bounded. If R is L2, both signals are L2, right? If R converges to 0, both will do, okay? And we try option 3 where V is designed as a function of R squared. And then we go to the stability analysis. We first take a time derivative. And then we can, in this E double dot, it comes with Q double dot inside. So we can substitute the closed loop dynamics here in the bracket. And that's the time that you can include the controller tau here to design the controller, right? Because you want V dot to be negative definite. But this structure is not negative definite. You need to find a way out, right? So we can design tau, maybe cancel out some nonlinear terms and create some feedback terms. And in the next few slides, in the next topic, we will also introduce cross terms. Okay, so here just let me ask you a question. So what will you design with this controller? You have all this stuff. The simplest way is to cancel this term out, right? This is the obstacle that prevents you to show V dot is negative definite, right? So the simplest way is in the controller here. You design this controller and put all these terms in a box and repeat here in the controller. And they have different signs, so they will cancel out. And after it cancel out, you also add a feedback terms. And this feedback term plays an important role because the minus KR here, which comes from the controller, with another R in front of the bracket, can make V dot to be negative definite. So that's the way we design this controller. This is probably the most simplest nonlinear controller design because everything is known. Remember, everything in the controller have to be known. So after you design this controller, you substitute into here and you regroup and cancel out some terms. You got V dot to be ND, right? So everything is great. V is PD, V dot is ND. You got a global asymptotic stable or global asymptotic tracking. And here only shows R converge to 0, and that implies using the previous the property in the previous slide implies both signal will go to 0 as t go to infinity. Okay. Right now we're going to introduce unknown parameters, system with unknown parameters. So what is unknown? M is unknown. You don't know the inertia. You don't know the length, the L, right? Which is associated with geometry of the link. So M and L are unknown. This kind of nonlinear system can become complex, and the controller can be more hard to design if you assume system parameters are unknown and maybe Q dot is unknown. Q dot is not measurable. You only measure Q, right? But you control Q double dots. If these two parameters are unknown, how will you design the controller? Everything changes, right? If it's unknown, let's go back to this slide. If n is unknown, okay, then your controller, you have to implement something that's unknown. How can you write a code to implement a controller and which is unknown, right? There's no way. So you cannot use that structure. The controller had to be redesigned. So how will you design a controller? First here, let's repeat. The objective is to tracking control. And we want the joint or the state Q to track a desired trajectory, QD, QD dot, and QD double dot. They are designed to be bounded. And they are known values because they are by design, user's choice. And want E to be bounded, at least bounded, but if you can find E converge to 0, that would be great. But because we are discussing the unknown parameters, sometimes the error could not go to 0. Okay, but at least you need to design a controller that can ensure the error will be bounded. Bounded means you still have some tracking error, but it's bounded. It doesn't go to infinity. Okay, the tracking error will be close to 0. This is also acceptable as a controller. So the step is the same. You define the error signal. Okay, take the time derivative, check if control input appears in here. And because here it doesn't appear here, because you only see Q dot, right? And from the dynamics, tau is equal to something, and it's a function of Q double dot, not Q dot. So you need to take one more time derivative until you see Q double dot, okay? Because Q double dot implies the control here, and only you apply the control, you can design it in a stability analysis. Let's design the robust control for unknown system parameters. Tracking control. Here's the problem definition. So let's define the error tracking signal and filter tracking error. Constant. Open loop dynamics according to that, we divide it by m on both sides of the equation. You got, and move the second term to the right. You got Q double dot equal to G sine Q. And that's a minus. So this is the open loop dynamics. And let's say we design a design controller as tau as a feedback term, KR, because R is now the filter tracking error. You can consider it as a new tracking error, okay? Plus robust terms to be designed, okay? And you substitute into here, back to the open loop dynamics, you got closed loop dynamics. Okay, this is closed loop dynamics. Something weird here, okay? Something weird here. Right? In the default function, we only see R or E. Yeah, in other words, only see the filter tracking error or the tracking error, not Q anymore. We don't put V equal to minus MQ squared, right? It's different, right? If you put this, means your intention to show is, okay, is ND, which means probably Q squared ND, right? And you're trying to show Q goes to 0, right? Agree, right? But here we are not doing regulation, we are doing tracking, which is this, right? We are doing this, okay? But every signal in the diagonal function will be eventually proven to be 0, right? So that's why if this is your objective, you should. That's why we design the error signal here, because we want error signal converge to 0 eventually. So that's why we design this diagonal function. The next step is take the time derivative of the diagonal function. And here you will see the time derivative of the signals, right? And there is no way either R dot or E dot give you the access to substitute your control input, right? To substitute your control input into here, right? To use this equation, there's no chance given this V dot, right? Because you find there's no Q double dot in here on the right hand side. 听得懂吗？你不是要把 control 带进去分析吗？因为你要设计 control 嘛，你要怎么设计就根据 V 大让它是 ND 嘛，所以你要把 torque 放进来嘛，你要把 control input 放进来，对不对？你怎么放进去？用这个 equation 啊，因为你知道有微分的地方就是有机会带进去嘛，因为你 V 大嘛，所以这边 signal 都微分了，那就是你唯一的 chance. Here's the chance because you have time derivative. Here's the chance that you can substitute the Q double dot where you have control input here. But there's no Q double dot. It's in R and in E. Why? So let's take a look. So we introduce open loop, closed loop. Now get into here. V dot is, we design V, start from V. V is right? And we take the time derivative, we got RMR dot plus alpha square M alpha square EM E dot. So we did not see Q double dot, right? But it's basically Q double dot is in here. So you need to expand this, which is, what is R dot? R dot, according to the definition R dot, you take one more time derivative, you got R dot equal to E double dot, E dot, right? And here it comes with Q double dot, right? Because Q double dot is inside E, okay? So when you take the time derivative, that's E double dot plus alpha E dot. And this is alpha square E and E dots. Okay? Then you expand this. That give you, which is QD minus Q double dot, right? Plus alpha E dot. Now you can substitute this closed loop dynamics here, and you got this, okay? Now it become clear how we will design this tau, this torque, right? Next step, by experience, is we expand this signal out, okay? Which is using this relation. because the reason is if you don't expand this, there's no way you can cancel these two terms. They are different. But after you expand, they can be canceled. Here, these two terms can be canceled. And that the reason is I expand eta here, so you can cancel this term out. Otherwise, there's no way you can cancel it out. So now, from step 5 to step 7, we are doing regrouping. You can cancel some terms, and some terms were left, and you can regroup the whole equations. So next, we also substitute our control into here. And this r is coming from this r in front of the bracket. Next, by observation. How do you observe? Well, you will see every term will have r over e, right? Because eventually you design your reliable function as a function of e and r, right? To prove v dot to be nd, you need e squared, r squared. So you want to create e squared, r squares. So by observation, r squares minus r squared is a good term. Plus something r squared is a bad term, but they can be combined, right? If I choose control gain large enough, maybe larger than alpha m, okay, they can be a negative. So it's r squared term here, and here is the minus e squared term. So it's highly likely to be good result for v dot. But problem is here. You see r, right? You see r. It's not r squared, it's only r. M is unknown, right? L is unknown. So basically, this term is unknown. So we can upper bound these terms, okay, by a constant C1. C1 might be large because it had to be greater than m times q d double dot. Q d double dot depends on the trajectory you're trying to follow. But it's reasonable that you assume you can upper bound this whole term because q d double dot is assumed to be bounded in the very beginning, right? The assumption here is q d double dot is bounded. So it can be upper bound by a constant. That's why you can upper bound the summation here by a constant. So we can upper bound the whole term in the bracket by a constant, positive constant C1, right? Agree, right? No matter it's negative or positive, it can be upper bounded by C1. So now there's another question. Let me repeat steps 7 here. So I have a question for you. MQ okay, this is step 7. So question for you. Can you design, this is originate from, this is basically U, right? This is U. We design U as this. And the design of this can probably prove this to be ND or at least an SD. Okay, and maybe you need to choose some gains, K, for example, K greater than alpha M, right? Because K, here's a negative term, here's a positive term. You need to choose. The gains have some conditions to be satisfied to guarantee stability, right? But can you design maybe another term called plus some terms that cancel out this term? Can you? Probably you want to do this, right? Can you? If you can, what would be the term in the bracket? You might want to, oh, here it has R, right? It has minus and R. Here it has plus R. So maybe you design this in the bracket, right? Okay. Now you might be genius, right? God, I never thought about this. You must be Einstein, right? So what's the problem with this? Obviously, it doesn't work. Why? You know why? 有人可以告诉我为什么不行？ So it looks great, right? It looks you are smart. instant, right? Next instant. But if you put this and this term can cancel out this term. Oh, amazing, right? Everything becomes square, and it probably will be ND, right? But it doesn't work out. Why? The problem is in the not in the analysis. Okay, the problem is not in here. The problem is in the control. Why? Remember, I say every term in the control in the U have to be known, right? You cannot implement something you don't know. If it's an unknown system, if you don't know inertia, you don't know the mass of the system, you don't know the mass of the car, how can you implement a controller that require that information? You don't know what's the mass of the robot arm. Can you put that mass in your controller implementation? No, right? If you are control car 10 kilo, okay, you want to apply a force, or in this case, maybe it's robot arm, right? We controlling this joint, we apply a torque and want to do something, and here is have inertia, okay, M or inertia here. In this case, it's M, right? But M could be generalized to inertia. Okay. Anyway, this is unknown system, right? And in your controller, you say controller can be designed as KR plus VR plus all this guy, right? The problem is I don't know M. I don't know the mass. How can I put? You need to implement this in your computer, in your processor, right? And this is the required parameter to be designed. You don't know the mass. How will you implement? So that's the reason we design this as a controller. Okay, we don't know this, but we let this VR take care of the uncertainties. Okay. At the beginning of this class, we say we can do that. You can do that because M is known, right? In the previous case, M is known, you can do that. And that's the most easiest nonlinear controller design, but not now, okay? So now we design the controller. Let's see how we can do the analysis. We can upper bound the terms. Now go back. How will you upper bound these terms? It's a scalar, right? V is scalar. Everything here is scalar. So scalar can be positive or negative. What's the upper bound? Can I say it's upper bound by, we know this is a, can be upper bound by constant, right? C1, which is positive, greater than 0. Okay, C1 is greater than 0. Can I say C1 is true or not? Well, I'll give you a counter example, okay? Negative, positive, negative. Sorry, negative. It's unknown, right? If this summation is negative, okay? Negative, but this time is negative, is still upper bound by C1, which is positive. That's correct, right? This upper bound is still holds, right? But the product of this will change the sign, right? So it's, if R is minus, R is the state, you cannot control states. And this is, if this is minus, okay, and R is minus, R here had to be minus, and you upper bound a minus start by C1, right? So it's correct term by term, R by R, this by C1, but the product will be different story, okay? So you cannot do that. But what is correct? If you do this, that will be correct, okay? Because the product will always be positive, right? But you need to do this because you don't know R is the states. It could be positive, it could be negative. You cannot control. You don't know because you don't know the solution, right? You don't know the trajectory of R. You don't know the solution. So that's why next step. Next step, I change equality to inequality and put absolute value on R and regrouping the terms. So we have minus R squared, and you need to choose. We have these good terms. This is good term. Right? Okay, but here there's a condition for it to be a good term if k is greater than alpha m. Okay? So you need to implement your controller k large enough, at least greater than alpha, which you can is a user choice. M is the unknown, right? Unknown mass. So, but it's still feasible, right? You choose if you control the robot arm, for example, right? And you can usually by design, you know, approximate mass of the link, right? So, for example, by observation, probably 10 kilogram, right? You can put the upper bound can be, you choose k to be alpha and put 15. As long as it's greater than 10, it will be fine. Okay. If it doesn't work, then you change to 20. Eventually, it will work, right? By the tracking area, you can observe. So that's feasible. Okay. So good terms. Now bad terms, which is positive, right? Always positive, because already put the upper bound, absolute value. So the approach now is to design this to dominate this. Okay, and VR, what is VR? VR, well, is designed to be some KR. Here is a constant. Okay, and the reason to design as this structure have some reasons. We want to use least robust term to deal with this term, right? VR is robust term. Robust term is used to deal with uncertainties. And where's the uncertainties? Here. And uncertainties can be upper bound as this. Okay, so robust term is used to deal with this. Although robust term VR is designed same as feedback control, right? Same as the KR here, the term before VR, right? They have the same structure, but the functionality is different. So that's why I put K3 C1 squared here. K3 C1 squared is another constant. And you will understand why I put in this structure in a few minutes. So let's do these two terms. Let's try complete square. Okay, so basically it's this. A is y squared by. In our case, there's a minus here. Okay, and want to use complete square to put into some minus square term plus some plus terms, okay, which is 4a b squared. Here is y minus ab. Okay, remember, right? 这样写有没有错？2 let's try this. Y squared plus ABY minus 对不对？plus 2AB squared, right? And plus 对不对？是吧？ So this equal to this, okay? By observation. Use that to upper bound these two terms. Okay, this term is minus K3C1 squared. You will understand in a few seconds why I put square here. R squared plus C1R. Okay? And you can consider this. Absolute value of R squared is equal to R squared. Okay? So by comparing, the A here is what? Is K3C1 squared. Okay? B here is not equal. Let's say this. B is C1. Y is okay, is equal to Y, which is R minus 2A, so it's 2A K3 C1 squared, and B, which is C1, okay, squared plus 4A 4K3 C1 squared B squared C1 squared. So it cancels C2 1 squared, C1 squared, so it's 1. Okay? And plus these two terms minus K alpha M R squared minus E squared. Okay? 这样 OK 吗 Okay, so this term is always negative, right? It's not E squared term, it's not E squared term, it's not R squared term, but it's always negative. Okay, so we can further upper bound a negative stuff by 0 and repeat whatever left. So 是 K3 minus K alpha M R squared minus okay. So same as this. How do you interpret this? This is constant, depend on K3. And the constant can be decreased by increasing K3. And if you don't consider these third terms, the first two terms can make the system negative definite, right? But when you have this term, it becomes UUB. And as we say, R will eventually be bounded. This can be used to conclude R will eventually be bounded. Because R and E is a signal in the above function. E and R will be bounded. Okay, so your tracking signal will be bounded. So now let's now plot the above function. upper bound is not equal. This term not equal to this. This term upper bound is. And can zero upper bound something that's negative? 可以吗 ？Zero 是不是可以 upper bound 任何负的东西？所以这个可以被 zero upper bound， 因为这里不是 equal sign， 它是 upper bound。OK，and you can drop it zero， 你就可以不写。So they become that. So let's plot V. So the initial condition of V depends on the initial condition of R, right? Depend on initial condition of E and the initial condition of R, and that E depends on QD0 minus Q0, 对不对 ？So sorry, let me again. So initially, you design some trajectories, like sine function trajectories. Okay, it's QD. Okay, and initially your Q is here. Okay, your Q0 is here. This is QD0. So the difference of these two is the air, right? This is the air. So air is here. E0. Okay? And you implement the controller, right? You implement these controllers in your closed loop dynamics, in your system, okay? And you get a closed loop dynamics. So you don't know the solution of Q, but you know the analysis tell you that E eventually will be bounded. So E eventually will be somehow bounded, okay? Bounded. You won't increase, it will be bounded, okay? But this bound depends on the selection of K3. If you choose a larger K3, this area will be smaller because, and you will track this trajectory, trying to track this trajectory, okay? This tells you what V value eventually will be, because V0 is from here and it will be UB, okay? And this value, this UB value determines what this is, right? Because there's a relation, E and R. E could be -2, so I should put this absolute value, okay? Because it's square here, okay? So given a V value, you can only find R squared, E squared, not R or E, okay? Only squares. So I put absolute value here. V is always positive, right? V is always positive because you have R squared, E squared. And when you trying to infer V to your error signals, you need to put absolute values because from here it's always positive. How do you find this? According to this, you know, approaching to 0, okay? The approach to 0, that means V dot is equal to 0, right? When it's in here, V is almost constant, right? 如果 v is constant, v dot will be 0. Although it's an inequality, you let this one to be 0. Okay, you want find v dot to be 0, right? To get this value. But it's the best you can do. It's not equality here, okay? It's not equality here, okay? It's upper bound here, right? It's upper bound. You only know the v dot upper bound, right? You don't know what v dot really is. You know the upper bound, but so the only thing you can do is set this to be 0, okay? And you can find where is r, where is r, where is e, okay? 我们把两个合在一起。So let's put let's further upper bound this by minus minima k2, and let's take the coefficient out, okay? And let's square plus. Okay. Let's combine E and R into one parameters. Okay, that's easier to find the upper bound of both signals. Okay, 听懂吗? And you have put minima here, minima of these two values. Okay, you compare the two, and if this one is smaller than this one, and the whole term, you choose the minima one. Okay, you choose K2. If this term is smaller than K2, you choose this one. 听得懂吗? And you put minima because there's a minus here, so that you can upper bound this inequality. And we put this one to be 0. That gives you z norm square to be right? 对吧? You put this to be 0. You put this term to be 0. Oh, right. This, right? It's hard to evaluate what E is, or what R is. The best way is to combine both to be Z. So you can only observe Z here. Okay. Okay, Z, but it can be considered as an error. Okay. And we now know this value. This value is equal to, the worst case, this value is equal to this. Make a square root. Take this square out. Okay. This is the value that's this is the worst case UB value. Worst case means V dot, this upper bound V dot, okay, is not equal, it's upper bound. And we put the upper bound to be 0, which means this is the worst case. We only know the upper bound of V dot, okay, and we put the upper bound to be 0. So this is the worst case, okay. In reality, V could be smaller than this, but this is the worst case value, the highest value, okay. So, and there are many physical meaning of this value, right? You see K3 here, K3 here. If you increase K3, this value will decrease, right? it will decrease, right? Means if you increase your control gain and VR here, K3 here, which is in VR, so you can make your Q more close to QD. 我要找 V， 它等于0的时候，这个它的 R 和 E 会到哪里嘛？懂吗？我要让这个等式等于0，我要去找最小的 R 跟 E 是在哪里。但你不 combine 在一起，我无法找出来。我知道 combine 在一起，这样我就可以求出它的解的嘛。You have two variables R and E, and only one equation. How can you find E and R? There are infinite number of solutions, right? So the way is put the two variable reduced to one variable, Z. Of course, you have to compromise something, but at least you know what Z value is according to the V value. You know what the Z value is. So the question is, if M can be measured, then what will happen, right? So basically, they change our assumption here. So they change the problem here, okay? So that will be the previous case with exam model knowledge. Okay? So the controller design will be easier.